Persistent objects. Object data must ultimately be stored in a database. This article shows you how. Persistent objects. In the last couple of articles we have introduced business objects and shown how simple relationships can be represented. The relationships expressed as object properties are a more formal and neutral representation of the relationships between data entities that can be implicit within the database design, or explicit within the database schema. Moving away from a data-centric view of entities and relationships to a more structured, object-oriented exposition has many benefits, but most languages, including Delphi, cater only for an in-memory object model. Objects have no state persistence capability unless one is provided for them. There are many design solutions to this requirement, and we have already established that the business problem domain objects themselves should not communicate directly with the database. An appropriate design is to have another set of classes that exist purely as an object interface to the database, and will be responsible for loading and saving problem domain object state. Our problem domain objects will know nothing about how their state is stored on disk, only that there is a particular class that is responsible for this operation. The business objects will make a method call onto such an object and delegate the work to it. The first decision that must be taken is to decide how to map objects onto a database schema. Although a number of object databases exist, most companies have standardized on an existing RDBMS with which they are comfortable and experienced. Promoting a development change to a more object-oriented approach is difficult enough without demanding that the typically large investment in a highly evolved database technology is replicated for a new, unfamiliar one. Therefore, this article will focus on mapping objects to a SQL-based RDBMS, as this constitutes the majority of installed development systems. It should, however, be stressed that one of the advantages of our object model is that it is totally architecture neutral and can be applied to a large number of different database topologies, including ISAM, and object-based ones. Mapping objects to databases. It is obvious and natural that there is a relatively simple conceptual correspondence between an object and a database tuple, record. Therefore, when storing object state in a RDBMS, a very common and practical solution is to map a problem domain classes to tables, objects to records, and properties to fields. Note that because our database will be storing object state, it must be a complete representation, and therefore it is likely that there will be more fields in the database table than a given class has public properties. In some cases a public property may not have a directly corresponding field, but the general principle is to map a property onto a database field of similar fundamental type, character, numeric, date, etc. Let us now extend our basic framework classes to support object persistence. Our problem domain objects, TPD object, need to permit other classes to force them to load or save their state. There are a number of alternative ways of approaching this situation. One is to force all objects to implicitly save their state before they are destroyed. In practice, applications require a finer degree of control over when object state should be persisted, and so our TPD object will gain two new public methods, load and save. The save method is parameterless, but our load method must define exactly which object is to be loaded from persistent store. Within our framework, all problem domain objects that have been saved are allocated a unique ID within a given context. This might be within objects of the same class, objects of the same ancestry, the application, or universally. We will use this ID as a parameter to the load method to standardize on the means by which we establish object identity. Note that this is always used, even if a specific class might have a suitable alternative primary key concept. Standardizing on a single concept of object identity is useful, as our framework can use this consistency to treat our problem domain objects in a generic and polymorphic fashion. Some might question the presence of a public property, albeit read-only, that exposes a type chosen for convenience to suit the internals of our framework. In practice, the identification of objects by ID is something that occurs almost entirely within the framework code and is rarely encountered within the actual application logic itself. Within that arena, objects are handled using concepts much more familiar to the end user, such as the set of customers called Smith, rather than through developer-oriented abstracts. Having defined a public method interface on our TPD object problem domain class, we must now consider the implementation. In fact, this is very simple. We have already stated that the business object knows nothing about how it is stored, only that there is another object responsible for this task. Therefore, the implementation of our persistence methods on TPD objects simply delegate the work directly to another object referenced within a private field. Each of these method calls is parameterized with self, so that the delegated object knows with which instance it is dealing. In effect, when a problem domain object is instructed to save, or load, itself, it simply instructs another object to save me. Data management. The task of actually saving the object state to a database falls to a set of classes in the data management layer. Predictably, we will have a class hierarchy allowing us to provide significant database-independent functionality. All of our classes responsible for data management will descend from an abstract TDM object class. This class provides an object-based, database-independent interface for database operations. Specific database support is provided by creating a concrete descendant of this class that provides a connection to the database of choice using whatever technology is appropriate, and additionally provides some base services. These base services will be totally customized to the specific features of the database concerned, and will be used by application-dependent descendants customized for handling a particular TPD object. This design does not dictate the means by which the TDM objects communicate with the database engine. Each database layer is free to choose the most suitable, easiest/fastest technology available. This might be ADO for SQL Server 7, IBExpress for Interbase, the BDE for Paradox files, a custom API, or indeed it is possible to interface to something like ODBC or Corba for generic handling. My preference is to optimize the connection using a database-dependent set of components, as these are generally offer the greatest functionality and speed. Note that selecting a database-dependent API does not restrict your application to running with this database. It is possible to substitute one database-dependent TDM object layer for another. The interface to the TDM object is purely object-based, so it can be guaranteed that, provided our database layers implement the concrete methods correctly, the application will run identically without changes. The actual implementation of each database-specific layer will depend upon the database concerned, but in general for SQL-capable databases it is worthwhile to provide a generic execute command that takes a valid SQL command as a parameter. Once we have a TDM object descendant for a chosen database, we must provide a number of descendants from this class, one for every TPD object in our application. These will be customized to handle a very specific combination of saving a particular class in a particular database. The details of these classes depend upon the features provided by the data management class for the particular database, but one feature is vital: the save operation must return the ID of the object saved. The reason for this is that in our chosen model, a TPD object does not have an ID until the first time it is saved. A particular benefit of this model is that it is very easy for the data management layer to detect whether it is necessary to generate an insert or update type database action. Typically, the allocation of the ID might be done by another object designed purely for this purpose, but there is an very beneficial optimization that can be made if we rely upon our data management object to do this task for us. Remember that our ID must be unique in a given context. If the context chosen is that objects of the same class have unique IDs, then this can be equated to records in the table having unique IDs. Most databases have some facility for generating sequential unique IDs for inserted records, and make this value available after the database update. Using this facility within our data management layer can avoid replicating the effort to guarantee uniqueness, and in the best case can save on extraneous database operations to establish the next available ID. If the chosen database lacks such features, then an internal ID allocator scheme within the data management hierarchy can be used. Listing 1 shows the extensions to our framework unit to support load and save operations, together with the outline of a class to handle data access to a database through a do. It is assumed that the do connection has been established and that utility routines are provided within the class to execute SQL commands and to handle back the received data. In this implementation, descendant classes are required to override the load method, and also to provide a new insert and update implementation. It is fairly easy to see that these three methods should generate appropriate SQL code and update the object from the result set, or vice versa. With a bit more effort, it is possible to place more work within the generic TADO_MObject class itself, imposing a more rigid interface on descendant classes that requires less implementation. An example of this would be the ancestor class generating SQL commands dynamically, given a set of property names and values. Our class-specific data management objects, such as tCustomerDM, corresponding to tCustomer, must have intimate knowledge about the internals of the PD object for which it is responsible. In this sense, they can be viewed as friend classes of the problem domain object, and in Delphi this means that the implementations must be in the same unit. This articles' problem our design requires a TDM object to be provided for every TPD object. Where and when might this provision take place? What is this issue with this approach, and, by analyzing the pattern of method calls to our TDM objects, how may it be circumvented? Listing 1, Data Management Objects and Interfaces, Unit Framework, Interface Type TDM Object equals class, tpd object equals class private dm object, tdm object, fid, t object id, public procedure load, const id, t object id, procedure save, and tdm object equals class public procedure load, pd object, tpd object, const id, t object id, virtual, abstract, function save, pd object, tpd object, t object id, virtual, abstract, and tado underscored mobject equals class, tdm object, private fadu, tado express, protected // Features to assist descendants to interact with the database procedure execute, SQL, string, property ado, tado express read fadu, // methods that descendants must provide function insert, const pd object, tpd object, t object id, virtual, abstract, procedure update, const pd object, tpd object, virtual, abstract, public function save, pd object, tpd object, t object id, override, and implementation procedure tpd object load, const id, t object id, begin assert, dm object nil, no data management. Object available, dm object load, self, id, and procedure tdm object save, begin assert, dm object nil, no data management object available, fid equals dm object save, self, and function tado underscored mobject save, pd object, tpd object, t object id, begin if pd object id equals note assigned, then begin result equals insert, pd object, and else begin update, pd object, result equals pd object id, and listing 1, next in series.